In today's video, I want to show the process of calibration of a BOONTON RF millivoltmeter. This is the model 92B, probably similar to for other models. Anyway, I have the instruction manual here on the iPad, and on chapter 5, which is maintenance, we've got the periodic calibration procedure. So because I moved from one house to another new one, I even changed country during the transplantation. They didn't care very much, and when the instrument arrived, it was sort of bent. Luckily enough, it was not damaged. The boards inside, these two boards, were bent, but seems like nothing is broken. I have checked already. Now it's not bent anymore because I managed to fix it and put it back in shape. Anyway, so I want to recheck. It looks like, because this was calibrated by me before, but it looks like now is a bit off. I want to recheck the calibration. So we'll go through that now. There are some conditions to follow to the calibration. Those are all stated here in the manual. One is, for example, the room temperature and the 5 minutes time on. Now it's been on for a while, so no problem there. So let's jump through the first steps. Adjustment number 1. We check the minus 15 and plus 15 supply voltages, and we check those on the main amplifier board at C119 and C118, and we adjust R143 or R140 to put the voltages in range. I have already checked that the first one was spot on. Second one was still within the tolerance because it was 14.99, so it was like 0.01 difference, and the tolerance is plus minus 0.1. So but I put it on plus 15. Okay, so these are the caps. We are looking at the bottom part of the instrument, just beneath the transformer. These are the caps. That is, the one on the left is the one for the plus 15 voltage, and if you look carefully you can see it printed on the board. And the one on the right is for minus 15. And the two resistors, variable resistors, are those the white ones, the ones you want to move to play with to get the right voltage. So let's try and put the multimeter on the plus 15, for example, and we can see that we've got 15006, so that's fine. Let's move on the negative 15, and we've got minus 15001. So the first two steps are okay. Now we go to the third step, which says to set the range to the 1000 millivolt range, so 1 volt, and measure the chopper frequency at test point 13, and adjust our 244 for 94 plus minus 1 hertz. So 244, we have a schematic here on in the inside of the top cover. 244 is this tripod here on the right, or what is that? This one here. That's 244, and point 13 is this point here. So we go on the 1 volt range, and we send 1 volt signal. So I'm sending now 1 volt RMS over 50 ohm. Frequency is 350 kilohertz. I choose this frequency because for calibration, I think that's enough. They say that's a reliable, that what is needed is a reliable source between 200 and 500 kilohertz with less than 1% distortion, and it levels up to 3 volts across 50 ohm. So I'm in the middle, 350 kilohertz. So let's put the multimeter on to measure the frequency, and let's give it a 1 volt signal there. Let's put it on. We've got the definitely got the signal. So I'm gonna check here on the point 13, and what we see is a frequency of 93.8. So that is good enough. That is good enough, close enough to 94, so no problems there as well. Now the next step is to set the full scale range selector to 1 millivolt range, which is the lowest one, and zero the instrument, and then set the 30 millivolt range and adjust 233 for a zero reading on the recorded terminals on the back panel. So first of all, we want to check that when the instrument is off, we've got the needle at 0. Okay, so it looks like it's fine. Now we switch the instrument on, and we try to zero the instrument. Now I have some issues with this instrument. I have noticed, probably, unless I have some issues here with the environment, because there are some peaks on the lower range, like if it captures spikes. Anyway, we try to zero the instrument, and to zero the instrument you have to move the pot here and try to get an average zero reading. So I'm gonna adjust now the pot a little bit so that it fluctuates just up and down around the 0. Let's try a little bit less. It's very sensitive, and I'm not sure if anybody knows more about it. I'm not sure if this is the normal behavior, but to me it looks like a little bit too much of a movement. Okay, too big fluctuations, I would say. So anyway, we try and get around 0, and then we switch to 30 millivolts, and we connect the terminals on the back. So we connect that one there, and we go over DC voltage. We connect this one as well, and we read for 0. So this is minus 0.02. So I think I will not bother. That's okay, and the instrument is indeed over 0, so I think this is acceptable. Let's see the next step. The next step is gonna be to the step number 6. Set the full scale range selector to the 1 volt range and apply 1 volt, and adjust our 353 for plus 10 volts at the recorded terminals. So we want the 1 volt scale, 1 volt signal, and 10 volt on the multimeter. So let's see, 1 volt scale, 1 volt signal, which is there, output on, and we want 10 volts. So we've got 10.3, and in fact the instrument is over 10. So if you look at the upper scale, that will reflect the DC scale on the terminals on the back panel. So if we were over 10, we would read 10 as well there. So in fact they agree at some, in a certain way. In fact, as I said, this is more than 10, is indicating more than 10, that is indicating more than 10. So let's go to R353, which we want to look here. You can look in the manual, but we've got this simple schematic. So R353 is this one here on this board. So is this one here, the 1 millivolt. Let's see if I can put this in the shot. Yes, I can. Okay, now I'm gonna adjust. Obviously, I'm in the middle, so I'm gonna adjust to get the 10 volts. Okay, it's a bit critical, but this is a multi-turn resistor, so it's doable. Okay, that's good enough. That is done. Let's have a look at the needle. Now the needle is a bit below 10, so let's see what we do next. So after we have done that, we go to the adjustment number 7, step number 7. Set the full scale range selected to 1 volt and apply 1 volt and adjust R179 for 1 volt indication. So now we have the same condition, but we want to adjust R179 to get 1 volt indication on the meter this time. Okay, so R179 is this one here, which is gonna be this white one here. This one here. So let's have a look. If I can, I'll put the screwdriver and we'll try and measure this one here. There you go. 1 volt, spot on. And still we've got the 10 volt reading, 9.999. That's okay. We can readjust that a little bit. Just a touch. That's fine. It's just jumping around. It's not really needed. And try to get as precise as possible. That's it. Anyway, that's fine. Okay, so let's go to the let's recheck this one. Let's go to the next step now. Step number 8. Set the full scale range to 3 volts and apply 3 volts and adjust R363 for 3 volts indication. Okay, so 363 is this one here, 363. It's the one on the right, which is it's marked on the board as well, 3000 millivolts. So we want to inject 3 volt peak to peak. Let's see if I can do it with this one. I don't remember. 3 volt RMS. Yeah, we can do it. 3 volt RMS. And let's go to the 3 volt scale, and I want to adjust now this guy here. Okay, and I'm gonna concentrate on the needle as I tune the pot. So I need the 3 volts. So now we're looking at the bottom scale. All right, there you go. All right, there you go. It's perfect, I would say. That's it. This is done as well. Next, adjustment number 9. Set the full scale range selected to the 1 millivolt range, zero the instrument, and apply 1 millivolt. Adjust 303 for 1 millivolt reading. So now we go down to the bottom of the range, and 303 should be the first one. It is indeed 303, and you can see those are also well marked on the board. So 1 millivolt, we go, let me switch off the signal gen there, and we go to 1 millivolt, and let me set it up, let me set it all up. Okay, so basically now I have to zero the instrument to 1 millivolt range, and then we input 1 millivolt and adjust the 303 as I said, and then in turn we'll go through the next ranges. We go to the 3 millivolts, to the 10 millivolts, 30, 100 and 300, and we do all the same things, just we will use the appropriate adjustment over the board, which will be 1, 3, 10, 30, 100 and 300. Then we stop here. We will have finished because we started with 1000 and 3000. So now I'm just trying to zero the instruments, but as you can see I have some I don't know, it picks up something, so it jumps around sometimes, as you can see. I don't know why. I still have to figure out the reason for this. So when it's difficult or basically impossible to zero the instrument, then it's also difficult to calibrate the scale. So I'll try and see if I can do this off camera and then come back with the results. Okay, now I have finished the calibration procedure, and let's go ahead and check some spot frequencies and spot levels. So let's go this time on the dBm scale. So let's put, for example, minus 20 dBm. Well, first of all, we come back to 350 kilohertz, and we go to minus 20 dBm. Okay, let's crank it on. Should go to 0. And it goes indeed, as you can see. So that's perfect. If we change the scale now to the upward one, we should get over -10, which is the case. And if we now take, for example, 10 dB less, we go to -30, we see that we go over the -10, and switching scale, we should go to 0. And those are the fluctuations at the lower ranges. The issues I have with the instrument, but by the way, apart from that, it is calibrated. So let's have a look at 0 dBm now. 0 dBm, but I want to now change the frequency. So this probe works from 10 kilohertz, let me just 10 kilohertz to 1.2 gig. So why not to go to 10 kilohertz at 0 dBm, and let's see how it goes. Still reading 0 dBm, so very good. Let's go a bit further down, just to push it. Let's go over 9, now at 9 kilohertz, 8 kilohertz, 7 kilohertz, 6, 5 kilohertz, 4, 3, 2, 1 kilohertz, and now let's go 900 hertz, 800, 7, 600 hertz. So we are -3 dB at 600 hertz. So that's good performance. Let's go the other way. This generator goes up to 25 megahertz, as you can see here. So let's go up to 25 megahertz, still on 0 dBm. And yeah, 0.1 dB off, so that's good. It could be the generator as well, I don't know. That is new. It's got a certificate of calibration, so I trust this instrument enough. Now I will jump over this to crank the frequency up to 1 gig. Okay, so we were on 25 meg. Let's go to 25 meg from the Marconi 2022E, 0 dBm. This also was calibrated against the HP power meter, so this should be good enough as well. Let's see, 0 dBm, and we are yeah, 0.2, just a little bit, just short of 0. But let's now go up in frequency to, let's say, 100 meg, and we've got 0.4 less. I will now jump up in frequency in steps of 100 megs, like this. So we go to 200 megs, and I will stay with the camera on the meter. That's 0.5, almost 0.6 less. 300 megs. It's going a bit down. 400, 500, 600, 700, 800, 900, 1 gig. Now, obviously, there are a sum of errors. One is from the voltmeter, one is from the Marconi. Obviously, the RF power meter, which I use to calibrate the Marconi, has some errors as well. So, yeah, I would say that's a good result. And in fact, if you notice up here, there's a table which gives you all the informations for the accuracy. Over the different ranges and frequencies as well. So the accuracy is always 1% of the full scale plus, depending on the range. So now we are, for example, on the 0 dBm, so that's 300 millivolts. So we are here in this first line, 300 to 3 volts. So we've got 1% full scale plus 1% reading in the lower part up to 50 kilohertz. Then it's 1% reading also up to 150 meg. And then it becomes 3% reading up to 7 meg. And then you lose quite a bit in accuracy, because here we have 10% of the reading up to 1.2 gig. So in effect, if you go in the 1 gig frequency, you've got this quite big error. So considering we were always between 0 and -1, I think -0.8, I think that's a good result. Anyway, that's all. I don't want to make this video too long, more than what it is already. So thanks for watching once again, and all the best, 73. Just for the sake of completeness, I have switched on the test set also, and I'm checking with the HP. I was doing it for myself because I was wondering how is everything working after some time. So at 1 gig, the 2022 is connected to this power sensor 8482A, and with a power of 0 dBm, we switch it on 1 gig. Let me check the frequency here. It's 1 gig, yes. So switch it on. We've got -0.2 dBm from the Marconi 2022 Echo. So 0.2. So let's see what the power sensor think about the test set. The test set now is hooked up to the BOONTON probe, so we could actually check the BOONTON reading at 0 dBm, 1 gig. So RF gen on, 0 dBm, and it goes to -2. But I know that this test set is not very linear with frequency. Going up and up to the edge, it drops a bit the level. So we now check the test set with the power sensor, and we go back with the BOONTON probe to the 2022. Okay, now the BOONTON is hooked up to the 2022, and the power sensor is connected to the TNC port, which is the bottom one. We'll check also on the N port. The specifications are not exactly the same from manual, from Marconi, but we check both. So 1 gig, 0 dBm. It was reading -2 on the BOONTON. Let's switch the gen on. Let's see what the HP thinks about it. -1.96. So, as I said before, it's not very linear with the frequency. The tolerance would be, I think, within 1.5 dB. So that's just slightly off. sitting at minus 2 dBm. So actually the BOONTON was reading quite right, huh? Let's check this end port now. When you switch the end port, the level drops automatically to -7 because this port is capable of up to -7 dBm, while the TNC port is capable of up to +13 dBm. So let's check -7, or let's do an even number. Let's go to -10. -10. So we set the range 1 down and we switch on the gen. Before it was -1.96, so now it's -1146, so it looks to be 1.46 below the level it should be. So it's this case is within tolerance, actually, just on the edge. Okay, so why not to check the this one with the BOONTON. Originally with the power sensor was -0.2 dBm instead of 0. So let's give it a carrier and 0 dBm, 1 gig. And we've got a reading of -0.4-ish. And it's very close. It's very close considering all the errors that you need to take account of. Also the error for the frequency correction. So I think that's perfect. Well, that's all. That's all actually. I think I have checked everything. And now I want to see if I can calibrate a little bit better the output level from the test set on the higher frequencies. That's all for now. Now I think that is really over this video. Thank you once again for watching. All the best.